Hi, everyone. Well, now I'm really standing between you and drinks, so it's going to be really hard. So I will try to keep this short. So my name is Zhang. I am founder and the CEO of a startup called AutoCore. We're a 7-year startup. Coincidentally, I'm also the co-founder and chairman of the largest autonomous driving open source organization called AutoWare Foundation. I want to thank you for Ambassador Ishi-san, Ito-san, and Jerry for inviting me to come to this event. I actually used to attend some of the HL session before while I was in the CTO office of Linaro. But having listened to some of the great talk today, I want to present something probably a little bit different. So what I'm about to talk about today is instead of some of the deep technical details which many of the presenters have done today, we look at it from the other end. It's how we put in everything, the great work everyone has been doing together in the OSS community into a real SOP product. And hopefully that will give you some of the insights, or at least some of the hints in terms of what we are actually requiring from the other end. And this is obviously in combination of the open source technology and also our proprietary technology to be able to satisfy the production demand of the OEMs. So this picture, probably a various of which has been shown in different OEM Tier 1's presentation already. On the top left is what we see the traditional E architecture, which in a typical passenger vehicle, you're looking at between 100 or 120 of discrete ECUs. In the middle and also in the right, what we are hopefully, everybody's moving towards, right, represented by Tesla, is in the Tesla Model Y, you are seeing the reduction of those 100 to 120 ECU to 25. So that is a big deal. That is a big deal, but it doesn't come free. Because the simplification of the hardware, the wiring harness, the connectors, the reduction of the ECUs are at the expense of the increase of the complexity of the software in each of those concentrated or centralized ECUs, which handles one or more functional domains across one or more functional safety requirement standards from QM all the way to ACLD. So this looks pretty elegant, right? The one on the right. And that's what's, just to remind myself in terms of what the title is, the curse of a zonal architecture. It does not come free. We see all the real headache in the deployment phase. And we also know these are being faced by many of the OEM, including Volkswagen, alike, that because of the software issues, which causing delay of the launch in face of trying to simplify the E architecture. It does come with benefit, otherwise we wouldn't do it, right? The reduction of the BOM cost, reduction of the wiring, increase of the power efficiency because it got less wires and the ECUs in the system. So this is a summary of the challenge we have seen so far. These are not challenges which I imagine it myself or my team. This was what we collected during the interaction with our customers, OEM Tier 1, so to speak. The introduction of the centralized computing. Well, I mean centralized, I don't just mean by the big box in the middle, by all the consolidated zonal controller, centralized computing, HPCs, the domain controllers. We are introducing single point of failure now, because just imagine you consolidate all the discrete ECUs. Previously, if one ECU failed, that function failed. The wiper didn't work, so it be. But right now, if any of the centralized computer doesn't work or fail, and you probably wouldn't shit yourself, but you will face a lot of functions, more than just one. So how do we deal with that? Software complexity. So as I said, the previously MCU-based discrete component, ECU components, is complex. We're dealing with over 100 million lines of code per vehicle, typically. But it is safely estimated by 2030, we will be dealing with 600 million lines of code per vehicle, if not more. And also that complexity is what I mentioned earlier, is not only we are dealing with the pure lines of code increase, but also we're dealing with trying to deal with multiple different level of functional safety code on one same piece of hardware, or even more so, one piece of silicon. Latency and bandwidth bottleneck. This is actually less intuitive, but if you look at on the, probably this one, how does this work? Yeah, probably just point and use my finger, easier. If you look at the introduction of the zonal controller, because now you are connecting all the actuator sensors to the ZCU rather than all the way up to the domain controller. That actually implies you need a high bandwidth and also deterministic bus than just a CAN. So that's why you see the introduction of the TSN capable of Ethernet in the new EEA. It's not only because it looks, it gives you flexibility in terms of deployment, but it's because that high way is necessary for a lot of cross-domain applications. Power and thermal management, security vulnerability, transition cost legacy. This is actually a big one because we want you to move from the left to the right, with a flick of your fingers, but it doesn't work like that because a lot of, from the OEM and Tier 1, they have a lot of legacy system to maintain. So what we see is that we have to, when we design a new software to support a new EE architecture, you have to be mindful, not because of introduction of the new software or the legacy parts, the radar, the sensor, the legacy counterpart of ECUs will stop working or cannot be OTA'd anymore and cannot be diagnosed anymore. And a standardization gap, this is something which I'd like to probably talk a bit later on, is we do see a lot of standardization body comes up. We are trying to actively participate in as many as we want or could, but the thing is that some of the effort are not actually divergent. So the approach we have taken is a practical one. Is we look for what actually is necessary for getting the production over. Now, this is how we optimize the total cost of ownership by utilizing HL and Zephyr, which I put in the bracket there, because I will be talking about two different types of a zonal controller. One type of zonal controller is, the next graph we'll probably see, is that you got more power, more juice from the silicon you use. So that's likely to be MPU with a SoC. So you have multi-core, big core and small core, not just the M core or R core in the ARM's world. On the other hand, you still have a multi-core MCUs coming up, from Infineon, from ST Micro. So that's what we see. We tried with Zephyr, but I have some comparison in the later slides. Not because we want to see how good we are, but it's because we want to see actually open source approach based on Zephyr actually brings some intuitive benefit compared with other approach. Now, we talked about some early presentation talked about application platform, talked about certification, module design, but actually what I wanted to say is that in our practical work, getting to the right fast and early is what's actually going to help the SOP timing. What that means is that just have a solid base OS or BSP does not work for actually those SOP program. You have to consider what does it take to get in that controller always also integrated with other controller on the same EE architecture. So I just want to show these two slides first. One is CCU and another one is ZCU. So I want to put this into perspective. Oops, sorry, what did I do? So that picture on the top left is what, again, abstract level, how we are seeing the new EE architecture is moving towards. You have one or two or more centralized computing units, which could be known as HPC. That could be found, based on, for example, latest Qualcomm A775, NVIDIA Store, Renesas Gen 5, etc. And then you have a multiple zone. It could be. We have seen 2, 3, 4, 5 different number of zonal controller in the vehicle. Regardless, abstractly speaking, we are looking at two main entities now in the new vehicle. This is not just actually in some of the Chinese OEM, which my face might tell you that that's where the part of the world I come from originally, but also actually in the new range of Mercedes-Benz, Volkswagen, Stellantis, Brain. You find that example anywhere, Renault with Ampere are working on. But this is where the complication happens. The zonal controller is not what looks like or what we thought. It's one type of zonal. It's not, actually. There are distinctly 3 generations of zonal controller. People can mix them up. The first generation is what we first seen in the market is that zonal controller now represent taking care of the body control functionality, gateway, power distribution, and simple I/O control with dealing with all the actuators. But the chassis and the wheel control are dealt with separately. That's what first come up. And then we're moving towards the second generation. By the way, each different generation requires different silicon capability to support them, and also different software capability. Second generation is where everything come into the zone, right? And people think, hey, why don't we just put everything down there together here? So you got central computing deal with ADAS and AVI, and you got T-boards hanging on the connectivity, and everything else is in those zones now. Body, chassis, network gateway, power distribution, wheel control. This is in the latest vehicle we helped to deliver in BYD and Chang'an, the two top Chinese OEM. That's like that. But actually, still moving, the world still changing. In particular, in the latest 48-volt supply. You probably, some of us probably come across because that has been one of the main push and also one of the innovation which Tesla was also spearheading. In that, and then you got a much more powerful central computing SoC supporting body, wheel control, chassis, IVI, ADAS all in one. Again, looking at the example of the Snapdragon A775, you will see what I mean. And then you got much more simplified zonal controller now. So this is the most complicated zonal controller, second generation. The first generation is a bit complicated, but much simpler than this. Then this one, you will find that the zonal controller becomes even more simpler than the first generation. And also, but the effect of this is that even though this is a lot simpler, it contains a lot of logic, which to simplify all the counterpart of downstream actuators. And small ECU, that is eventually how you help to reduce the overall BOM cost of the vehicle, not just the controller itself. Oops. This is a signal, me talking too much. Now, so CCU, so I promise I will go through the faster later if I run out of my time. Some of the key slogan here, high performance heterogeneous computing, communication architecture, multi-domain integration, mixed reality task execution. As I said, we're looking at executing from QM all the way to ACOD, different reality tasks on one piece of hardware, or even more so, one piece of silicon. The other side of the world, which is a zonal controller. So we talked about what the central computing need to take care of. Now the zonal controller, regardless which generation is, they will have to deal with this downstream device management, power distribution, 12 or 84 volt architecture of the counterpart of components. The thing is that in this picture is what we have used AGL. We started by using AGL addressing IVI and cluster, obviously. Then we move on, starting to utilize that as a base for ADAS. Then we're starting to move towards centralized computing, or prototype of that. Then we're starting to push that into a zonal controller. When I say zonal controller, that's a two flavor. We used AGL in the flavor where the SoC is required. When the MCU is required, we employ the Zephyr, which I will show that later on. So this is a typical MCU-based zonal controller. Typical example of silicon, you can use IH A50, Infineon 38797, 397, NXP S32K, and ST Stellar. So you've probably seen this stack. This is nothing like AGL. This is a typical AutoCore classic, right? You see that on every ECUs we've seen today. But one of the problems with this is not because of the AutoCore classic is bad. It's because it does not satisfy the job the zonal controller needs today, from the first generation to the third generation. For example, we all know AutoCore classic is a static linked code, right? You can't change that on the fly. And also, if any of the hardware change, you have to deal with all the Macau stuff, from scratch. Now, we have managed to design a software architecture that integrated with a Luna engine, which in one of the early presentation I also heard, created more or less like a virtual machine and a file system. In this, why we call it standardized is this type of framework. You do not need change of the zonal controller AutoCore classic stack, but you can redefine it by sending the bytecode from the central computer. And that, if your I/O doesn't change from zonal controller, you will have a brand new zonal controller without modification of the hardware or Macau. Okay, so that is actually quite interesting work and has benefited a lot of our tier one suppliers, because so they do not have to customize one revision, two revision, all different type of variants when there are slight requirement change from the OEM. Now next, I talked about the CCU solution, right? This is our, again, 3,000 feet. This is what our software overall architecture looks like in the centralized computing unit, and that is obviously highlighted. Is what we did based on AGL. Then we have a system service, SOA communication layer, deterministic runtime across the entire vehicle, function layer, and the SDV APIs in a SOA format. But one interesting bit here is the LLM-based orchestration engine. We probably don't have time to dive into this today, but I heard one of the early presentation. So this is our attempt in terms of in a centralized computing unit, all the tasks, no matter which traditional functional domain comes from, it will all go through our AI-driven large language model engine. Then the task will be separated onto each different controller, where it should go, and what type of functional safety requirement those tasks are, what type of stability requirements, those services need to be. And this turned out to be a very, very effective resolution to solve the, handling the mixed criticality workload on the same piece of hardware or silicon. So I won't read through this conscious of time and don't want to bore you. But if you're interested to talk, to find a bit more, we're happy to talk about those. So those are the end result, how we'd be able to develop the CCU and ZCU's turnkey software solution based on the open source low-level OS, such as AGL and Zephyr. When we talk about turnkey solution, we can't miss the fact that we have to look at the functional safety design of the entire system. We also can't ignore that how we actually deal with the system-level security mechanism. These are the parts which have to be dealt with at each layer of the stack. And again, when I say each layer, it doesn't mean just in the kernel, doesn't mean just in the BSP. Actually, all the way up to the stack, and to work coherently, provide the security capability and also functional safety. Obviously, those two are slightly different, are not interchangeable. But those have to be dealt with. And on the note of that is our stack has been product certified to ACLD and also security certified to ISO 21434 already. So last, I've got 4 minutes left. So last is a comparison. I know putting up any kind of comparison is risky, right? You don't know who you're gonna piss off in the audience. But please don't take this as saying Eclipse Open BSW is not good. It's just because we took the approach, we take advantage of Zephyr for the MCU-based ZCU system software. We inherited a lot of benefits to provide an alternative solution to traditional AutoSAR Classic for those ECUs. And also on top of that, we can demonstrate that to achieve a high functional safety certified ZCU system software has nothing to do with whether you're AutoSAR Classic software or not. Okay? And some of the benefits you see here, I won't resolve them. For example, multi-core support. AutoSAR Classic stack is notorious to be not multi-core friendly, right? And this is what Zephyr-based, actually RTOS, comes really handy, be able to handle multi-core support intuitively. Then if you look at the protocol stack, actually, there's a lot more things we can do. For example, on the CAN protocol stack, it's probably on par. But if you look at the latest, as I said, TSN-capable Ethernet backbone, the Zephyr-based RTOS is clearly winning over. And that you will find those IPs in pretty much all the new multi-core MCUs coming up, supporting the Ethernet backbone. So yeah, that is something which we thought would be interesting for you to look at as a comparison. Again, that is not to say the open BSW is not a great initiative for Eclipse Foundation, but what we're trying to say is that when we choose not to be bounded to a biased selection of what software stack to use, but focus on how we get to the quality certifiable production system, then actually there's a lot more choice out there, including what we have chosen in terms for AGL and Zephyr. So I think I've got 2 minutes early, so thank you for your time, and hopefully that we found slightly different. Thank you. I don't know if there are any questions. 1 minute to take.
Anybody have any questions?
Thank you for the detailed explanation of the work. I would like to know more about how you can support for the much more physical damage of the systems, like zonal architecture sometimes implies that the zonal controller is located in the belly for side of the vehicles, and it's possibly damaged by some incident from the side of attack. I mean physical side the collisions, and it would be very, very difficult for us to place those kind of zonal left and the right hand side type of things. And it also makes the system fail recovery type of fail-safe type of executions much more complex than the central architecture. So how you can manage those kind of things?
Great, thank you, Murata-san. First of all, is that you've probably seen the dark line here. I know this is probably not very clear. In the TSM capable TSM Ethernet backbone, so there is a technology which we have implemented called ERPS. So ERPS, so with available of the ERPS, you would be able to create a single ring or double ring redundant network topology. What that means, if any of the zonal controller here failed, for example, the back zone will get bumped, right, or power lost, what we have been able to achieve in the latest Q07 Chang'an SOP vehicle is within 15 milliseconds, every task being assigned or being predefined on the back zone controller will be taken over by the rest of the controller system. So that's the one way of dealing with it in terms of creating system level of redundancy for the controller failure. What I wanted to say, obviously, it will not be able to cover all the failure cases, but this is some of the design we can put in place in terms of introducing system level redundancy to avoid a single point of failure. Another approach which we typically do is you see instead of one CCU, you've got two CCUs, standard AB redundancy, but that's actually a very expensive approach. Very expensive because those boxes probably cost you about, 2,000 USD up onwards. Now, what the approach we have taken is we treat the entire vehicle, for example, this graph on the top left, as a distributed networking computing environment. Okay? Distributed network computing environment. What that means is that all the tasks, either is a BCM control or chassis control or telemetrics functionality or IVI or instrument HMI, those service becomes a task. We define those as a task. Those tasks are allocated onto a global runtime, not in the AutoSAR concept as in local runtime, only carry about one silicon resource. But this global runtime has the view of the entire main ECU capability, health condition as well. So that is the mechanism can support when you have one or two or defined criteria, maximum amount of ECU failure, those tasks within the defined period, within defined functional safety acceptance criteria can be reallocated onto the remaining functional controllers. But obviously that, you can't have the full failure if you have the powers, of the all zone controllers down or being smashed. But that does give a lot of reassurance to prevent a single point of failure in terms of probability. So if you are interested in that, we can provide more detail in terms of how that implementation is done. This is actually part of this functional safety solution. I know this doesn't offer you enough detail, but that is indeed one of the instances we put a lot of effort in. Failure of the zonal controller, because as you said, those could happen and quite often.
But if you want to make some migration tasks from the left-hand side to right-hand side, if something about in the left-hand side,
Yeah.
but you may be able to learn the kind of fail recovery type of executions of tasks, but you have to keep the synchronization of the status of those kind of things all the time, right?
Yes, you're absolutely right. So the one of the main difficulty in that scenario is to have the data, all the sensor actuator data integrity. So that is quite difficult. I can't say we can deal with all the tasks. For example, if you have the task which is to be executed in the VCU, which is ACLC or ACLD grade operations, we will probably treat them as a first priority, because they have to be actually functional safe regardless. But if you are dealing with tasks which are QM or ACLA tasks, so those tasks and service will probably be coming later as a priority. But yes, to be able to keep all the data, for example, if you have the two front Zonal, the left one get smashed or power get dropped, then if you look at all the sensors and actuator connected to the front left, how fast those going to be migrate, or those task status being migrate and reboot up on the right, on the front left. In reality, is those higher level of functional safety ones will be coming up first. And if there's no remaining headroom, either CPU cycle or memory footprint to load the rest of service, then those ones will remain as failure.
Thank you. I really understand.
Thank you.
Second question is okay? Okay. Second question. My second question is, I'm not able to see the detail of the expression about the third generations chart, but probably it seems that you put IVI and ADAS in the same box, same ECU. Is that right?
Yes. So in this version, we certainly in the central computing unit, there's IVI and ADAS, and also body, wheel control, and chassis in one big HPC.
Is that ECU? I mean, is that IVI is independently running on the ADAS? I mean, the different MCU or the associates used? Probably, I guess. Mixed quality of ADAS, the different ASIL criteria is pretty hard.
Yes. I mean, that's a very tricky question, but very good one. So I think what we currently see are two approaches. One approach is they put everything in one box, call it a one box CCU solution. But if you open that box, there are two separate boards on the same same motherboard backbone with a PCIe cluster. One board handling the ADAS, one board handling the IVI and HMI, right? But we do see some of the latest CCU controller. For example, the latest one, which was awarded just last week from Mercedes-Benz for their 2028. I'm not sure actually that even confidential, but so that is actually using a single chip. Okay, single chip. I think I slipped that. So there is a single chip solution coming up, and there are actually, I think right now we see potentially there are three silicon companies can offer the same chip. Running the IVI and ADAS in one as Qualcomm, NVIDIA, and Renesas. Obviously, we haven't got our hands on Renesas Gen 5 yet, so we don't know for sure that's going to happen. I hope we do very soon. But at least from the silicon specification and IP capability, that looks like it's capable. But we do see that, and you're right, Murata-san, you're absolutely right. Is handling this, the difficulty is exactly in the software.
Right. Yeah. I strongly doubt that a single chipset could host these kind of different aspects of safety critical systems with QM type of things. Because, for example, the cooling functions of the chipset
Yep.
as a single point, could be a single point for failure.
Yep.
So it's really hard to manage by software, I think.
Yeah, I wish I could disagree with you, but I couldn't. So I don't think that's a solved problem. I don't claim we have that solution either, but that's kind of a work in progress. And you're right that most difficult things, for example, in one of these Qualcomm A775 ECUs we were working with Bosch with, is exactly that. They're trying to migrate some of the previous ADAS and their IVI into one silicon on different VMs, obviously powered by hypervisor from QNX, in one controller, one silicon. That's definitely not without challenges. But thank you for the question. All right.
Thanks.
Thank you.